Okay, let's take a look at this problem. A sample of gas has a volume of 2.8 liter at an unknown temperature. So here is our sample of gas, and it has a changeable volume because it has this piston on top of it. And the pressure inside here is going to be constant. It's going to be the same pressure as atmospheric pressure. And we see this as a closed system, so the number of moles of gas is going to stay the same. When the sample is submerged in ice water at 0 degrees Celsius, so we change its temperature, its volume also changes and decreases to 2.57 liters. What is the initial temperature in Kelvin and in Celsius? Assume constant pressure, and we're also going to assume that the number of moles are the same. So the very first thing we want to do is we want to write down what we're given to give us a visual as to what we're dealing with. We're given an initial volume and a final volume. We don't know what the initial temperature is. That's what we're solving for, but we are giving an initial temperature. Now, I know, because I had a very good chemistry teacher, that I can't do anything in terms of math while my temperature is in Celsius. So I'm going to add 273 degrees to my, or 273 to my degrees Celsius, and I'm going to come up with my Kelvin temperature. Now I'm ready to do my math. Well, what math am I going to do? Well, I'm looking at an initial volume, an initial temperature, and I'm looking at a second temperature or final temperature and final volume. So I know that I'm going to use Charles's law. So the first thing we're going to do, let me get out of red. First thing we're going to do is we're just going to plug in to this equation. My original volume is 2.80 liters. My original temperature, I'm just going to call X. Okay, we're going to call that X in this case. And then my second volume, 2.57 liters, and my second temperature, 273 Kelvin. Okay, now I'm going to solve this using 060 math. So if you are proficient at algebra and you want to solve this your own way, go ahead and solve it however you see fit. If you're a little unsure of how to do this, you can always use the Math 060 method, which is to cross multiply. So 2.80 liters times 273 Kelvin, bring down your equal sign, is equal to 2.57 liters times X. Okay, so we cross multiply first, and my calculator, when I plug in 2.8 times 273, that gives me, where's my pen? Here's my pen, 764.4 Kelvin times liters. I've got to keep track of my units. And that is equal to 2.57 liters times X. Now, X is my unknown. That's what I'm solving for. So what I'm going to do, after we cross multiply, and I'm going to get out of my pen so you can, different colors so you can see what I'm doing. After we cross multiply, this is the results of our cross multiplication, I'm going to divide by my 2.57 liters because I want to get my X all by itself. So I'm going to divide by 2.57 liters, divide by 2.57 liters. Now we see my units of liters cancel out, and on this side of the equation, my numbers and my units cancel out because anything divided by itself is 1. So now I have X all by itself, and when I take 764.4 and divide it by 2.57, I get 290, where's my pen? 297 Kelvin. I'm going to circle this. Okay, now notice I have Kelvin because my kelvins were left over from my multiplication here. They didn't cancel out. Now, I want to ask myself, does this answer make sense? Let me change my pen color up here. We decided based on our math, that our initial temperature was 297. Now we know that volume and temperature are proportionately dependent on one another. As one goes up, the other goes up. So when my volume went down, my temperature should go down. So yes, this makes sense. If I was originally at 297 degrees Kelvin, that's higher than 273 Kelvin. Now, we're not quite done with our problem. The problem wanted to know the temperature in Kelvin and in Celsius. So my Kelvin temperature was 297, and then my degrees Celsius, I'm going to take 297 and I'm going to subtract 273 from it. So 24 degrees Celsius, which, by the way, is about room temperature.